We're pulling off a heist today, legally stealing the exact examiner mark scheme for Cambridge IGCSE Physics 0625. Zero fluff right now. We're going straight into the exact strategies that stand between a B grade and an A star. Think of this explainer as your own visual memory palace. We're going to lock these required high-mark answers into your brain for good.
Here is the brutal reality. You probably know the physics concepts, right? You know what speed is. You know what acceleration is. But then you sit in the exam hall, stare at a curved motion graph, write what feels like a perfectly logical answer, and when results day comes, 0 marks. You completely blow your grade boundary on the exact wording. It's a massive confidence killer, and honestly, it happens to the smartest candidates.
Why does this happen? Because ordinary revision totally misses the point. You're busy studying the physics, but you aren't studying the examiner. Seriously, one vague word or one missing unit, and boom, marks instantly lost. We are going to fix that painful learner mistake right now by getting inside the examiner's head. You have to stop explaining concepts like a student and start hitting those specific triggers like a grader.
Enter the high-mark framework. This 4-step process is your ultimate quick win to guarantee top band marks every single time you see a data graph. Step 1. State the core concept. Step 2. Pull your evidence or data directly from the axes. Step 3. Provide the scientific reasoning. And Step 4. This is the absolute game changer. Use the exact examiner wording. Lock this simple formula in, and data analysis questions basically answer themselves.
But before we can actually apply the framework, we've got to memorize some concrete rules for extracting data. On a distance time graph, it's straightforward. The gradient is your speed, and a flat horizontal line just means you're stationary. But you have to be incredibly careful here. The absolute second those axes change to a speed time graph, the entire rulebook slips. Now the gradient is your acceleration, a horizontal line means constant speed, and the area under that curve gives you the distance traveled.
I cannot stress this enough. Never ever mix these two up. The gradient dictates entirely different physical properties depending on your axes. Literally, one of the biggest traps students fall into is reading a speed time graph as if it were a distance time graph. You've got to check those axis labels the very first thing every single time you turn the page.
Okay, let's see how this builds by diving into a real Cambridge-style example. We're looking at a pretty complex parachutist case study, where speed is plotted against time during a free fall. This curve is packed with different data points, from A all the way down to G. The gradient is constantly shifting, which tells us that the acceleration is constantly shifting too.
In a moment, I'll show you the examiner clue that changes the answer completely. But first, you need the framework that makes that clue obvious. Because if you just look at this curve and casually say, she goes fast then goes slow, you are leaving guaranteed marks on the table. We really have to break this down point by point.
So you have to ask yourself this key question at every single corner or point on the curve. When a graph line changes, what new description or calculation is actually needed? The answer depends entirely on the physical context. You are telling a story using physics. Every time that gradient shifts, the physical reality of our parachutist has completely shifted. Let's trace the story from A to D. At point A, she just starts to fall, right? Her speed is increasing, so she's accelerating. By point B, the curve is getting shallower. Her speed is still increasing, but a bit more slowly now, meaning the acceleration is actually lower. Then, at point C, something critical happens. She hits her maximum speed, and the line goes completely horizontal, staying flat all the way until point D at 28 seconds. This flat line brilliantly illustrates terminal velocity. That right there is the exact examiner wording you need. Between points C and D, her speed is completely constant at 40 meters per second. The gradient is 0, which means her acceleration is 0. You absolutely must use the phrase terminal velocity here to secure that mark. And notice it happens again later on at point F, where she reaches a new, lower constant speed, a new terminal velocity. But here comes the twist. At point D, she pulls her parachute. Boom! This creates a downward sloping line, which represents a negative relationship. As time marches forward on the x-axis, the values on the y-axis for speed rapidly fall. This steep drop from D to E to F, and again at G when she finally lands, requires some highly specific descriptive language.
Look closely at how the physical context shifts here. At point D, the parachute just burst open. The air resistance is massive, causing a super rapid drop in speed, so your examiner wording has to be high deceleration. But as she slows down by point E, the curve isn't quite as steep. Here you must explicitly state that the deceleration is lower. When dealing with Cambridge mark schemes, precision in your adjectives is literally everything.
Let's do some quick data extraction. 25 seconds. That is exactly how long she travels at her new, lower, constant speed of 5 meters per second. How do we know? The examiner might ask, for how long was the parachutist traveling at 5 meters per second? You find 5 on the y-axis, trace it over to the flat line, and see it starts at 35 seconds and ends at 60 seconds on the x-axis. 60 minus 35 gives you exactly 25 seconds. It sounds super simple, but under exam pressure, so many candidates just panic and write down 60. Don't fall for it. You have to actually do the math.
All right, let's test those mark scheme hacker skills with a quick spot the error challenge based on a real, very common student mistake. Imagine a question asks you to describe in words what happens to the speed and acceleration at point D. I'm going to give you a typical student answer, and I want you to figure out exactly why it scores absolutely 0 marks, even though it kind of makes sense intuitively.
Here's the flawed answer. At D, the parachute opens and she slows down. Now, it's conversational, and yeah, it's physically true, but it's not physics. It loses marks for being way too vague. Now look at the improved top band answer. At D, the speed decreases rapidly, resulting in a high deceleration. See the huge difference? It perfectly applies our framework. It states the specific variable and uses the exact terminology the examiner is hunting for. That is how you secure the bag.
So the overarching goal here is avoiding these fatal traps. Missing units or rounding too early will instantly kill your calculation marks. We've tackled vague explanations and graph axis errors today, but honestly, if you calculate that deceleration perfectly and forget to write meters per second squared, you lose the mark. If you write down a conclusion that isn't completely backed up by the data plotted on the curve, you lose the mark. Treat this checklist like your final scan before you dare turn the page of your exam booklet.
Okay, so you've successfully hacked the motion graphs. Awesome. But this explainer leaves us with a massive unresolved problem. You are still completely vulnerable to the traps hiding in practical data questions. You can extract data and calculate gradients all day long, but what happens when Cambridge asks you to design the practical investigation itself, or to evaluate the reliability of the data collection? That is a completely different beast, and it's where the grade boundaries truly separate the absolute best from the rest. The heist isn't over yet. We need an escape tunnel.
To unlock the next step and master the top band evaluation framework, you must subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. But before you click over to the next explainer, think about this. If your stopwatch lags by just half a second during every single reading, how does that invisible error completely warp the perfect curve we just mastered today? The heist on practical anomalies is next. I'll see you there. Stay curious.